All right, let's get started on Unit 3, which is the longest unit in Calc 2, so it will take a little bit more time. This is the sequences series, power series, and Taylor series. So we'll start off with section 5.1, sequences. So the definition for a sequence is quite simple. It really is a list of numbers. The only thing I would add to that I recommend you add as well is it's not just any list of numbers. It is an ordered list of numbers. So the order the numbers are listed matters. There is going to be the first one, the second one, the third one, the fourth one, and that order matters. Separated by commas is the comma notation with the curly bracket to represent the sets. And that ... there means that this is an infinite sequence. And then other notations that could represent the same thing. The subscript n is typically called the index of the sequence, or more commonly known as the counter. So it's keeping track of the first one, the second one, the third one, the fourth one, and so on. Sometimes we start at 1, so a sub 1, a sub 2, a sub 0. It's also pretty common to start at 0, so it might be written as a sub 0, comma a sub 1, comma a sub 2, and so on from there. Sometimes we start at a different value as well. Those are just some common starting points. A sequence can be generated in a couple of different ways. First of all, it could be a recurrence relation, which is the next term in the sequence depends upon the previous terms. And that's often denoted as a sub n plus 1 to simply mean the next one equals some function or something to do with the previous terms. And that's where each term is defined in terms of the previous term or terms. So it doesn't necessarily need to be all of them. It could be some of them. It could be one of them. Or it can be generated, a sequence can be generated by an explicit formula. That one you really think of as just a function. That's a lot easier to think of, but this would be discrete here instead of continuous because it's not a continuous connection of all of these. It's just the first one, comma, the second one, comma, the third one, and so on. All right, let's do some examples. So we'll list out, first of all, the first, let's say the 5 terms of this sequence. The first ones, I'm going to just denote really quick that this notation, the subscript n equals 0 to infinity, that means it's an infinite sequence starting at the counter of 0. Whereas this for part B over here, that would mean this is an infinite sequence that is starting at the counter of 1. And so that will be kind of defined for you. And you're going to see that where we start doesn't necessarily matter, but it does change things in terms of the values. So we just have to be clear when we're communicating, what do we mean? Where are we choosing to start? So here we're choosing to start at n equals 0, and then I'll sketch the graph of the sequence. So it really is going to be a sub 0 is equal to, this is given as an explicit function. So I can plug in 0, and I got 1 over 2 to the 0, which is just 1. And if I plugged in 1, I can, again, think of this as a function. 1 over 2 to the 1 is 1/2. If I plugged in 2, I would get 1 over 2 squared, which is 1/4. And you can imagine me doing that even farther. I'm not going to do all of the work for all of them, but I am going to list out the terms of the sequence. It was 1, comma 1/2, and then 1/4, and then maybe doing a little yoga for the brain. Can you imagine plugging 3 into that function? I would get 1 over 2 cubed, 1 over 2 to the 4th, etc., etc. So it looks like I've listed out the first 5 terms of that sequence. That curly bracket notation is going to be an important part of that notation in this class, and you'll see some examples of that. And that ... really is describing this as an infinite sequence rather than a finite sequence. A finite sequence would have an ending point. We would not have that ... This question also asked me to graph it, so we should do that as well. This is a discrete sequence. So there is not going to be some continuous line. We're not going to connect the dots. This is going to be the big difference between this section and previous ones. So I'm going to have an n and an a sub n instead of an x and a y. It's still the function notation. And it started off, it looks like I started off plugging in 0, and then I plugged in 1, 2, 3, 4, 5, and so on. And when I plugged in 0, I got 1. So you can think of that as graphing the ordered pair 0, comma 1. So I'll graph that ordered pair of 0, comma that height of 1. Think of that as the ordered pair. And then when I plugged in 1, I got 1/2. So that's the ordered pair 1, comma 1/2, and then 1/4 and 1/8, and so on. The main difference here is you are not connecting the dots. This is not a continuous function. This is a discrete function. Okay, all right, so now we've got that example. Let's do another one here, something that is alternating between positive and negatives. It's always good to sort of see the difference between them, so that will make our lives a little bit easier to get used to the patterns. So I'm going to go ahead and start off by plugging in 1 in this case, because it tells me to start at 1 instead of 0. If I plugged in 1, I would get -1 to the power of 1 over 1, which is -1. If I plugged in 2, I would get -1 squared over 2, and that -1 squared does turn into a positive, and that's what I meant by alternating. And then you can see me doing that for many of them. So -1, 1/2. If I plugged in 3, -1 cubed would go back to negative over 3, so -1/3. And then I can imagine what's happening here. Feel free to pause if you need to catch up there. But I just plugged in 1, 2, 3, 4, and so on. Don't forget the ... in that notation. Okay, so then in this case, if I were to graph that sequence, again, here's my n and b sub n. Remember, this is discrete. This is a sequence. I plugged in 1 and I got, so here's my 1, 2, 3, 4, and so on. If I plugged in 1, I got -1. If I plugged in 2, I got +1/2. And then at 3, I got -1/3, and then +1/4. And you can kind of imagine what's happening as this were to go on forever, because this is an infinite sequence. This is alternating between positive, negative, positive, negative, positive, negative. And the terms are also getting smaller. And we're going to have some vocabulary terms for that in this section as well, but it's good to start recognizing those. So for that part C, this is something that's a little bit different than part A and B of this example. This is not given as explicit. I don't have just something to plug it in. Instead, this is a recurrence relation or a recursive formula where the next term depends upon the previous terms. So I'm going to go ahead and start plugging in some things here. I already have a sub 0 in that example. So I know my a sub 0. So my next one would be a sub 1. And you can see from this formula, this a sub n plus 1 equals a sub n squared minus 1. Do a little bit of yoga for the brain here. This one's kind of tricky. I'm going to zoom in so we can all see this a little bit better. I want a sub 1 equals something. So I want my subscript to be 1, which means I have to look at this formula and what would my n be in order to make my subscript 1? Well, my n should be 0. If my n was 0, this would become a sub 1. So maybe that's like a little bit of off to the side, thinking it through. If my n is 0, then I'm going to get this formula to look like I want it to. And I wanted an a sub 1. And if my n was 0, this would become a sub 0 squared minus 1. And a sub 0 is 0 because that was given to me in the problem. So I got -1. Okay, let's do that again. That's tricky. The second time around, it'll make more sense. Now I want a sub 2. I'm just trying to find the terms of the sequence, one on top of the other. Now I want a sub 2. So I want my subscript to be 2. I look at the formula, the recurrence relation that I have. What should my n be to make that subscript a 2? Well, if my n was 1, then 1 plus 1 is going to give me the 2. So the logic there is I'm looking for an n equals 1. But if n equals 1 on one side of the equal sign, it must also be 1 on the other side of the equal sign. So then on the other side of the equal sign, I'm looking at my formula. That would become a sub 1 squared minus 1. And then I know what a sub 1 is because I already found it. A sub 1 was -1. So then I have a -1 squared minus 1, and I got 0. Okay, let's do another one. Third time's the charm. It's not easy. So these recurrence relations take some practice. So I want now an a sub 3. I want my sub, because it's just the next one. Yeah, okay, I'm just counting 1, 2, 3. It really is a counter. So I want my n subscript to be 3. So I look at my formula, I have an n plus 1 here. So that would mean I want my n to be 2. And if my n was 2, then this formula would have a subscript of a sub 3, which I want. And then that would give me, oops, got the wrong color. Let's try that again. A sub 2 squared minus 1. And hopefully from here, you're starting to see a pattern. This just means the next term is equal to the previous term squared minus 1. So if you think of it maybe a little bit more like in words, it might make more sense rather than having to plug in different numbers every time. You don't need to write down what numbers you're going to plug in. You can, you always can, that'll always work. But you can think of it instead in terms of the next term is equal to the previous term squared minus 1. That tends to be a little bit easier. Okay, we might as well finish that off since I started it. My a sub 2 was 0. Again, it was 0 because I found it in the previous term. And so then minus 1, 0 squared minus 1 is negative 1. And then I'm going to continue listing it out and actually drawing the graph there. So I'm going to go over here, my terms of the sequence. It started with 0. That's really important. The first one was given to me, but it's still the first one. So that still counts. The first one was 0, then I got negative 1, then I got 0, then I got negative 1. And I bet you can recognize a pattern. A big part of this section is to see a pattern. Like, what do you think the next one's going to be? Just recognize a pattern. It's the biggest part of chapter 5 is to recognize that pattern. It did ask us to graph this, so I'll go ahead and graph this as my n and a sub n. So at a sub 0, I got 0, so that's like graphing the ordered pair 0, 0. Then the next one was negative 1. So at 1, I got negative 1, and then it was 0, and then it was negative 1, and then it was 0. Don't connect the dots. Remember, this is discrete. This is just a sequence. This is not a continuous function. It's not a continuous function. It's just a list of dots. Yeah. So that's that. And then in this case, it does kind of look like it's alternating back and forth. This one looks like it's probably never going to settle down. Right? I'm going 0, negative 1, 0, negative 1, 0, negative 1. It'll never settle down. Whereas the previous couple of examples, if we scroll back and look, the previous couple of examples, I was going alternating between positive and negative, but they were getting smaller. They kind of looked like they were going to settle down to possibly a single number. Same thing over here. They were all positive, but they were getting smaller and smaller and smaller. They looked like they might be settling down to a single number. So we're going to talk about what that means today as well. Okay, let's do one more example, part D. Let's list out a few of those terms. So I'm going to do this nice and slowly. It tells me that the first term is 1, and it tells me that the second term is 1. This one started counting at 0. Sometimes we start counting at 1. Don't be surprised by that. You need to be comfortable going back and forth between them. But I've got a sub 0 equals 1 and a sub 1 equals 1. Now I have my recurrence formula. My recurrence formula is a sub n plus 1 equals a sub n plus a sub n minus 1. I'm going to do a little bit of work. I'm going to write some stuff down. You might write it down, or you might want to just watch and do it in your head so you can get used to this. I want a sub 2 because I already have a0 and a1. I just got to go in order, right? Order matters for a sequence. I'm just going to go in order. I want the next one. So my next one is a sub 2. So I want this subscript to be a 2. If I'm looking at my recurrence formula, I want that subscript to be a 2. The only way n plus 1 will become 2 is if n is 1. So maybe I make that little note to myself there that n should be 1. Okay. That's my dog Luna. She's a barker. Okay, sorry about that. Right, there's my n should be 1, but whatever you do to one side of the equal sign, you have to do to the other side of the equal sign. So my n should be 1 on both sides of that equal sign. So that will become a sub 1 plus a sub 1 minus 1. And we know that 1 minus 1 is 0. And then I also know those two terms. I know those because they were given to me. So I ended up with a sub 2 is equal to 1 plus 1, which is 2. So you might want to start to recognize a pattern here. What's happening? This says the next term is equal to the previous term and the previous term. So it's the sum of the two previous terms. So that's where I got to. Okay, now we've recognized the pattern. I bet we can just kind of plow through and do a whole bunch of them. So the next term is going to be the sum of the previous two terms, which is 3. The next term is going to be the sum of the previous two terms. The next one will be the sum of the previous two terms, and then the sum of the previous two terms, and then the sum of, sorry, that would have been 34. There we go, 34, the sum of the previous two terms, and I could keep going forever. This might look familiar. This was called the Fibonacci sequence. All right, now we have an idea of what a sequence is. Let's do a little bit more with the vocabulary on a sequence. I'm giving you some explicit formulas for a sequence and some recurrence relation for a sequence. Let's do it the other way around. Okay, I'm going to give you now the terms in the sequence, and you have to give me the recurrence relation and the explicit formula. Being able to work backwards is going to be very helpful here. So the first few terms in the sequence are given here. Find the next two terms. That just means recognize the pattern and find a couple more. And then I want you to find a recurrence relation and an explicit formula that will generate this sequence. Okay, so this part A right here, I've got 1, 1/2, 1/4, 1/8, 1/16. Recognize the pattern? See what's happening? Should be as obvious as it looks. The next one would probably be 1/32, and then 1/64, and then it would be 1/128, and I could go all day long. I've listed out the next few terms. Cool, I found a pattern. Now I do need to do the other two parts of this question, which is to find a recurrence relation, and it is called a recurrence relation. It's also called a recursive formula. So both of those are the same, okay? Whether you call it a recurrence relation or a recursive, whether you call it a recurrence relation or a recursive formula, you'll be just fine. They are the same. Okay, all right, so let's go ahead and do that. So the recurrence and recursive formula, that is the next term is equal to something to do with the previous term. So what do we mean by that? What's happening from one term to the next? I went from 1 to 1/2, and then I went from 1/2 to 1/4, and then I went from 1/4 to 1/8, and then I went from 1/8 to 1/16. What's happening each time? It looks like the denominator is getting bigger by a multiple of 2 each time. It's just doubling each time. But that's happening on the bottom of the fraction, so it's not doubling, it's multiplying by 1/2 each time because it's happening on the denominator. So that means that it is the previous term multiplied by 1/2. Now, for a recursive formula or a recurrence relation, you need to identify the first one. Because I started at 1, I didn't start at 3. If I started at 3, let me write this down just so you can see. If I did start at 3 and I had this same recurrence relation, then it would be cut in half, and then cut in half, and then cut in half. Those are completely different terms. So you have to define the first term of the sequence when you have a recurrence relation. Cool. All right, there's my recurrence relation. I'll circle that so you can see there was the other part of this question, which is asking for the explicit formula. So now I'm looking for the explicit formula. So let's do that. To find the explicit formula, what I have to do from there is think of it as a function. Think of it like a continuous function. It's not a continuous function. It's definitely discrete, but you want to think of it sort of like a continuous function. So I need my a sub n is equal to some function. What's happening? Like what formula is going to produce the numbers 1, 1/2, 1/4, 1/8, and so on. And so I'll give you guys a nice easy hint there. They're all 1 on top, so it'll be a 1 on top. And then they are all powers of 2 on the bottom. So that's 2 to the power of n. That's what powers of 2 look like. And then you have to also identify the starting value. Did you start counting at 0 or did you start counting at 1? So I'm going to write something down and it's going to be wrong, but watch why it's wrong. If n is bigger than or equal to 1, well, let's start off by plugging in 1. 2 to the power of 1 is 2. This would become 1/2, but I don't want 1/2 to be my first term. Remember, the order matters. I need 1 to be the first term. So in fact, in this case, I actually need to start counting at 0 because 2 to the 0 is 1. And then you can plug in 1 and I would get 1/2. If I plugged in 2, I would get 1/4 and so on. So the starting value matters. Ta-da. Okay, let's do another example. So the same question, which is find the first few terms in the sequence. Find the next, find the next 2 terms in the sequence, and then find a recurrence relation, and then find an explicit formula. So sort of the 3-part question. Let's do part B. First, let's list out the next few terms. I've got 1, 3, 9, 27, 81. Do you recognize the pattern of what's happening there? It looks like those are all just powers of 3. So 1 and then 3 and then 9 and then 27 and then 81, and I want to find the next power of 3. So multiply that by 3 and I would get 243. That was my next power of 3. And then what's the next power of 3 is 729. I just multiplied it by 3. Like literally you can just use your calculator if you want. I was recognizing the pattern. So 81 times 3 and that is 243. And then 243 times 3 is 729 and the numbers are getting bigger and bigger and bigger. Okay, and then we got to do the two separate things that we needed. One of them was the recurrence relation. Ooh, sorry, I should spell that correctly. Recurrence relation. There we go. Or you could call it a recursive formula. But that's the one where I need the next term is equal to something to do with the previous term. And in this case, I had to multiply by 3 each time. So I took the previous term and I multiplied it by 3. But remember, you got to tell me the starting value. In this case, I started at 1. I didn't start counting at 1. I mean, my first term was 1. Because again, what if my first term were, let's say, 2? I mean, it's not, but if it were 2, then I followed this recurrence relation, then I would end up with multiplying that by 3, and I would get 6, and then I would get 18. Those are completely different numbers, right? So you have to be very, very specific. You have to identify the first term in the sequence when you're doing a recurrence relation. Okay, and then let's do the explicit formula. The explicit formula, you want to think of that like a continuous function. So that's just that a sub n is equal to, that's really the main difference between the two of them. This one will be the a sub n plus 1. This will be a sub n. And that's more of a, could I have a function that I plug in 0, 1, 2, 3, 4, all the counters and get 1, 3, 9, 27, 81, etc. And we already said what it was because we already said they were powers of 3. So just 3 to the n. That one did not have fractions. And then I want to make sure that it works. You can always go back and check your work. So I want to make sure that this works. If I were to plug in n equals 0, that would give me 1. If I were to plug in n equals 1, that would give me 3. If I were to plug in n equals 2, that would give me 9, and so on. So it looks like I just needed to start counting at 0. Ta-da! If you wanted to, just for fun, to see a different way, there's more than one answer. This might be helpful as well. I could have said it was 3 to the power of, let's say, n minus 1. I could have. If I did that, then I would have had to change my counter to start counting at 1 because I still need my first term of the sequence to be 1. This was non-negotiable because it was given to me. So if I plugged in n equals 1 here, then that would become 3 to the power of 0, which is 1. And then I would plug in n equals 2, and I would get 3 to the power of 1, which is 3, and so on. So you can see that there is more than one answer to a question. And they are both perfectly correct. They are both identical. They just look different because I started counting different. They still have the same pattern. They still have the same pattern. Okay, and then we'll do one really quick that is a alternating sequence. So you can see that alternating sequence here. I have 1, and then negative 1/2, and then positive 1/3, and then negative 1/4, and positive 1/5. And then recognizing the pattern, I can see the next one would be negative 1/6, and then 1/7, and then negative 1/8, etc., etc., etc. So now that I have that pattern, let's go through and do the same thing. First of all, let's do the recurrence relation, a sub n plus 1. What do we think is happening there with that a sub n plus 1? It's kind of a little trickier. It looks like I'm taking the denominator and adding 1 to it each time. That's what's happening. I'm taking the denominator and adding 1 to it each time. This one will be kind of hard. Let me start off with the alternating. Let me deal with the positive, negative, and then I'll come back to the fraction. Fractions are tricky. Let me deal with the alternating. Just negative 1 to the end is alternating, just like we did earlier. It's going to give me positive, then negative, then positive, then negative, then positive, then negative, then positive, then negative. Okay, and then I also want to think about what am I doing to the previous term? I'm taking the denominator and adding 1. So I need to flip the fraction. I need to flip the fraction first. So if I were to do a 1 over the previous term, that would give me just the denominator. 1 over the previous term. 1 over 1/2 would give me 2. 1 over 1/3 would give me 3. So if I do get rid of the alternating part, that 1 over a sub n, 1 over the previous term, is just giving me the 2, 3, 4, 5, and so on. And so then I just need to add 1 to it each time. And then I have to flip the fraction again, this was trickier, to keep it a fraction. And then remember, we had to identify what your first term was. So my a sub 0 was, what was it, 1? In this case, that very first term. And then we could always double check, because what if I missed a negative somewhere, right? Maybe I missed a fraction somewhere. You should always double check. So if my a sub 0 is 1, then my next term would become, I would need my n to be 0 to get that to be, let me write that down. I want an a sub 1, so I would need my n to be 0. But if my n was 0, this would become positive. So I missed a negative. So I should go back and make that -1 to the n plus 1 to keep it alternating in the correct way. I need my next term to be -1/2. So then this would become -1 to the power of 0 plus 1, which is 1, which is positive. That's what I want. So let's write it down in the right color. -1 to the power of 0 plus 1 times 1 over the absolute value of a sub 0 plus 1. So this would become a -1 over 1 plus 1, which is -1/2. We're good. And if I wanted to do one more, I could check one more. If my n was 1, then this would become -1 squared. And then this would be a 1 over the absolute value of -1/2 plus 1. So that denominator definitely gave me 3, which is great. And then times a positive 1 over 3, positive 1/3. We're good. Okay, so that was me just checking my work. So I'm actually going to erase that, since that was me just checking my work. So now I have my recurrence relation. The other part of that question was, of course, the explicit formula. Sometimes the explicit formula is a little bit easier. That's the a sub n. I still need it to be alternating, right? Didn't we say we still needed that to be alternating? And alternating is always going to be a -1 to the n or a -1 to the n plus 1. And I still need a fraction for all of them. They're 1 over. Yeah, and they're 1 over just the counter, because the denominator was the same as the counter, right? 1, 2, 3, 4, 5. The denominator was the same as the counter. And I should start counting at n equals 1. And then I should realize one more time, if n is 1, that gives me 1, which is great. But that would make this guy negative, and I need my first term to be positive, so I should adjust that to be -1 to the n plus 1. So there is my recurrence relation and my explicit formula. Okay, so now we have a whole lot to do with sequences, which is great. Now the next thing we have to do is limits of those sequences. So the limit of an infinite sequence, we've just decided to shorten the vocabulary. What we actually mean is the limit as n goes to infinity. If I say find the limit of the sequence, what I really mean is the limit as n goes to infinity. So that's maybe what we should write down. That's kind of the new vocabulary. So find the limit of the sequence. That just means the limit as n goes to infinity of your sequence. Okay, that's the vocabulary. And then what we also have is this idea of whether it settles down or not. Remember when we first started graphing those first few, some of them settled down, some of them kind of were alternating all over the place. So if it settles down to a single finite number, if that limit exists as a single finite number, then we say that the sequence converges to that number. Very similarly to when we did improper integrals in Unit 2 in Chapter 3.7. If the terms of the sequence do not approach a single finite number, like if they shoot off to infinity or they just go 0, -1, 0, -1 forever, then we say that the sequence diverges. All right, let's do an example. Write out the first 4 terms of the sequence and then find the limit of that sequence. If possible, describe your reasoning wherever we can. Okay, let's first list out the terms. For me, the negative exponents are hard to do in my head. So I recommend you rewrite it as a fraction. Fractions are a little bit more visual, but that's a personal preference. So that's up to you. Let's list out the first few terms. It tells me to start counting at 1, so I'm going to start counting at 1. So a sub 1 is 1 minus 1 over 10 to the 1, which is 1 minus 1/10, which is 9/10. Okay, a sub 2 is 1 minus 1 over 10 squared, which is 99 over 100. And if you're using your calculator, which you absolutely can, and it's encouraged, then you'll probably leave it as decimals, which is totally fine. You would get 0.9, and then you would have had 0.99. So if whether you do fractions or decimals is up to you. I'm just a fan of fractions. They make more sense to me, but you could totally do this as decimals, I promise. So I got, what did I get? 9 over 10 as the first one, and then 99 over 100. Maybe you're using your calculator, maybe you're doing some arithmetic in your head. I got 999 over 1,000 for the third one. I got 9,999 over 10,000 for the fourth one. I found the first 4 terms and I wrote it down with the correct notation, including the curly brackets and the dot, dot, dot. And then I have to find the limit. So to find the limit, it's probably, sometimes at least, going to be very obvious. You got to let the obvious ones be obvious. There's going to be times where it's just, you look at those numbers and what is it getting closer to? This is 0.9, and then 0.99, and then 0.999, and then 0.9999. It should be pretty obvious. That's obviously approaching 1. Is it ever going to get there? No, but the limits don't really care what happens when you get there. They only care what happens when you get close. So we are doing the limit as n goes to infinity of the sequence, and we can just see that it approaches 1. That's the answer to that. If you wanted to write it instead using the Calc 1 logic, which is also fine, you would take the limit of each of those pieces of the function separately, and 1 is just 1, and then 1 over 10 to the power of a really large number. So as n is approaching infinity, this denominator becomes really, really large, like a billion or a trillion or 7 gazillion. So you have $1 on top, $1 on top, and a bazillion friends. Yeah, you're all broke. That's how that goes. $1 and a million friends, everybody's broke. That's just a fancy way of saying that that limit goes to 0. Yeah, so then it ended up being 1 minus 0, which is, of course, 1. So maybe you can just see the logic from the sequence. If that's the case, go for it. You're fine. Maybe you prefer to think of it the Calc 1 way. If that's the case, go for it. You're fine. All right, that's how we find the limit of a sequence. So let's just keep practicing. A sub n is equal to -1 to the n over n. Let's list out the terms of that sequence. And I'm going to actually jump right into listing out the term of the sequence. I'm not going to show my work. I'm going to do it in my head, which is okay. Let me start off by plugging in 1. If I plugged in 1, the numerator became -1 to the 1, which is negative, over 1. So -1 over 1 is -1. Now I plug in 2. -1 squared over 2 is positive 1/2. Now I plug in 3. -1 cubed over 3. And then now I plug in 4. -1 to the 4th over 4. This should look familiar. This is still an alternating sequence. I just happen to have the negatives in the opposite spot as what I did 2 examples ago, but it's still that same recurring alternating sequence. And then this one, I'm going to do the same thing. I'm just going to do a little bit of yoga for the brain. Let's take the limit as n goes to infinity of -1 to the n over n. You can imagine, and it really is as obvious as it looks. It was positive, negative, positive, negative, positive, negative. But it was settling down. Those terms were getting closer and closer to 0. So I really do have a limit of 0. Does it ever get to 0? Technically, no, but remember the limit is still equal to 0. We say the limit is equal to it. That's the definition of that limit from Calc 1. Cool, let's do another one. Okay, so we're just kind of practicing along the way, seeing if we can recognize some things that might happen. So for this one, I want to do this example, same kind of idea. This one's a recurrence relation. Let's list out a few terms, and then let's see if we can find a limit. That's what we're trying to do. We're going to list out a few terms and see if we can find a limit. So I have a sub n plus 1 equals 2.7 a sub n times 1 minus a sub n. I have the first term for a recurrence relation that was necessary. So my first term of the sequence is 0.4. The next term of my sequence, I'm going to do a little bit of work off to the side, would be 2.7 times the previous term times 1 minus 2.7 times 0.4 times parentheses 1 minus 0.4. I got 0.6. I'm going to write it down. 0.648. Okay, so the next one that I need to do is I need to do 2.7 times my 0.648 times 1 minus my 0.648, because this recurrence relation says that the next term is equal to 2.7 times the previous term times 1 minus the previous term. But what you can do, since you already have that 0.648 in, hopefully you guys can see it. You might not be able to see it with the screen sharing, but I already have it in my calculator saved there. Maybe I can change this a little bit. A bit better so that everybody can see it. Sorry about that. There we go. I'll try to edit that out. Okay. So now I'm going to do that 2.7 times the 0.648, but I can use the answer button in my calculator because it already has 0.648 stored, and then times parentheses 1 minus, I'm going to use that answer button because it had 0.648 stored. And I got let's write that down, 0.6158592. Now I can just press enter in my calculator again because it's using the previously stored answer button. It's using the previously stored answer button. So now I have the 0.63876, and then I'm going to press enter again, and I have a 0.623016, and then press enter again and 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 again. And maybe I could just do a whole bunch since I have my calculator out. And then you start to see it settling down. That's kind of the beauty of being able to use your calculator like that. Some of you might use an Excel spreadsheet, but the calculator will be the fastest way. And it kind of looked like it settled down, huh? And it went on and on and on and on forever. And it looks to me like the limit as n approaches infinity of this particular sequence, which we have it labeled as a sub n. If you wrote a sub n plus 1, that would be fine. Either or is sufficient for that recurrence relation. But we are going to make an estimate. We just used our calculator, and it looks to me like it settled down to 0.62962629. There it goes. Yeah, 629629, etc. Probably went on and on forever. That's our good estimate. Ta-da. All right. So now we have sequences as well as limits of sequences. Okay, let's practice some more. Yeah, it is kind of a lot. This section's heavy. This section is going to be heavy. Let's do this next example. I'm going to hopefully see it. There we go. Suppose a ball is thrown upward to a height of 20 meters. Each time the ball bounces, it rebounds to a fraction 0.5 of its previous height. Let h sub n be the height after the nth bounce. And then I've got a couple of parts, part A and part B to this. First, we're going to find the first 4 heights of the ball. And then we're going to find a general expression. And this is what we should write down. When I say general expression, I mean explicit formula. All right, we can do it. So I'm going to just first find the first few heights. So for part A, it really is going to be as obvious as it seems. So for part A, we're going to use H as the notation for this. So instead of A sub n, we're calling the sequence H sub n. So the notation would be H sub n. And I'm going to say, let's start counting. It doesn't necessarily matter, but I'm going to start counting at 0 because this particular one chose to start counting at 0. Okay, then let's list it out. We don't need to list out all of the work. We can do this in our head. It starts off at a height of 20. That was given. And then the ball falls and it bounces back up to 1/2, 0.5 of its previous height. So that would be 10. And then it does it again. Then it rebounds back to 1/2 of its previous height. And then it does it again. It rebounds back to 1/2 of its previous height. And then it does it again. And can you kind of imagine what's happening? What happened was the ball went up and then it went down and then it bounced back up and then it went down and bounced back up. And you can sort of see that it's going half the height each time. Eventually, gravity's going to win and it will settle down to a height of 0. We can see that. Let's do a couple of things. I found the first 4 heights. I'm now going to do part B, which is the explicit formula for H sub n. So now you don't really need to be thinking about this ball bouncing anymore. What you want to now be thinking about is these numbers. We need a pattern for these numbers. I started at 20, and then I multiplied it by 1/2, and then I multiplied it by 1/2, and then I multiplied it by 1/2, by 1/2, by 1/2. So I started at 20, and then every single time I divided by 2. So every time, so each time got an extra divided by 2. So I have a power of 2 on the bottom. And remember, for the explicit formula, you need to tell me where you started to count at. We started to count at 0. It's worth it to double check. Plug in 0. Do you get 20? I do. Plug in 1. Do I get 10? I do. Plug in 2. 2 squared is 4. 20 divided by 4 is 5. Plug in 3 and then plug in 4 and so on and so forth. And you're going to see that that does really work here. And now I know the question didn't ask, but if it did, the limit of this sequence is 0. It settles down to 0. Okay, so a couple more limits. Let's just practice with some limits. This is going to be a really good practice, so we're going to do a ton of limits in this unit. A lot of this has to come from L'Hopital's rule from Calc 1. So you do have to remember a lot of that from Calc 1. Let's just practice. Take the limit as it is. So I'm going to take the limit as n goes to infinity of 2n to the 4th over n to the 4th plus 1. From Calc 1, you can see I ended up with an infinity over infinity. So I can do L'Hopital's rule. This is still Calc 1 type of stuff. All the limits that you learned in Calc 1 are still true. So now I can do L'Hopital's rule. And L'Hopital's rule, remember, if you have an infinity over infinity, that means you can take the derivative of the top and bottom separately, not the quotient rule, the derivative of the top and bottom separately. And then you can simplify. In this case, those ends really do cancel. Sometimes the limit is easy. Those ends really do cancel. And I ended up with 8 over 4, which is just 2. So now I have the limit of that sequence is 2. Cool. Okay, so now you have some simple limit practice from Calc 1. Let me do one more, just a regular limit from Calc 1 practice. It's going to be the same idea. So I'm looking for the limit as n goes to infinity. It's always going to be as the counter goes to infinity of 1 plus 2 over n to the power of n. And then you'll start to do a little bit of yoga for the brain, and you'll notice that 2 over a really large number goes to 0. Remember, $2, a million friends, you're all broke. So that guy goes to 0. But inside the parentheses, I still have a 1. So 1 plus 0 is 1. To the power of infinity is not 1. It's a common misconception. 1 to the power of infinity is not 1. 1 to the power of a number is 1. But infinity is not a 1, or is not a number. So this is, in fact, an indeterminate form. So we got to do some L'Hopital's rule. So here is a good trick about L'Hopital's rule that maybe you remember from Calc 1 or when you did the 4.8 homework earlier on this semester. But this one's tricky. This is called the ln trick. That's what I call it anyways. I call it the ln trick. So I'm going to do a brand new limit. I'm going to use L for ln. Okay, and what I'm going to do, completely unrelated to the original limit, a brand new limit, I am going to randomly, and it really is a brand new limit, completely different. I'm going to throw in an ln. Because you can't just do that. You're not allowed to just throw in an ln. So this is a different function. I threw in an ln. It is completely different. I did change it. I will unchange it later on, but I want you to know that right now I did change that. This is a completely different limit. Okay, then I can bring that n down out front. That's properties of logs, and this becomes the limit as n goes to infinity of n times ln of 1 plus 2 over n. And then remember, L'Hopital's rule is there's a requirement for L'Hopital's rule, and that main requirement is it has to be a fraction. So I'm going to first turn it into a fraction, and the easiest way to do that is to take n to the power of 1 and make it n to the power of -1 on bottom. Then I can notice each separate one, top and bottom, have their own limit. 2 over a large number goes to 0. So this numerator becomes ln of 1, and ln of 1 is 0. So I got 0 on top. And then the denominator, this n to the power of -1, maybe in your head off to the side, you are reminding yourself that that means 1 over n. And as n goes to infinity, $1 a million friends, again, we're all broke. Okay, so that still goes to 0. Now I have 0 over 0. Now I really can do L'Hopital's rule. LHR for L'Hopital's rule. You might have called it Bernoulli's rule. It's often called Bernoulli's rule. Bernoulli is the mathematician who should have gotten credit for this, in my opinion. All right, so then this is going to become the limit as n goes to infinity of, I get to do the derivative of the top and bottom separately. So the derivative of ln, don't forget the chain rule. Okay, I have that written down, but maybe I should remind you. 2 over n is 2n to the -1, and then I brought the -1 down and subtracted 1 from the power. Okay, and then the derivative of the bottom separately, let me highlight that if you guys are watching that, n to the -1, I bring the power down, subtract 1 from the power. Okay, and some things cancel. Yeah, some things cancel. So this is going to become the limit as n goes to infinity of 2 over 1 plus 2 over n. I'll highlight what canceled. I think the n to the -2 and the negative canceled. And then 2 over a really large number goes to 0. All that worked for 2, which is great, except for, remember, that was me doing a completely different limit. I had changed the original limit. My 2 was the answer to when I had thrown in the ln. So I need to undo that ln. So the only way to undo the ln is to do that inverse. So of course that becomes e to the power of 2. So the limit of this sequence was e to the power of 2. Ta-da! All right, we're doing really good. We have a couple more for 5.1. I know it's a heavy section. We can do it. So this next little bit for 5.1 is going to be just definitions. So the definition of non-decreasing versus non-increasing. And yes, that is an annoying definition, but you will get used to it and you will start to see examples where using the words non-increasing and non-decreasing are in fact a better way to describe things versus decreasing and increasing. So non-decreasing is when every term of a sequence is greater than or equal to its predecessor. Non-increasing is the other way around. So why do I care about the non-increasing and non-decreasing? So think of the sequence 1, 2, 3, 3, 3, 4, 4, 4, 5, 5, 6. This is an infinite sequence. This is not strictly increasing because sometimes it was staying the same. So that's what we mean when we kind of use the words non-decreasing instead. So this is a sequence that is non-decreasing. It is not strictly increasing. Sometimes it was holding steady. So we use the vocabulary non-decreasing for that one. Okay, so now we have that one, and similarly for the non-increasing, I'm sure you can imagine that. And then the other vocabulary term there is monotonic. Think of monotone, real boring. Monotonic is, it means it's not going up and down and up and down and up and down and having fun. It's just kind of only going up or only going down. So real boring. And then bounded, a sequence is bounded if all of the terms are less than or equal to some finite number in magnitude. So this sequence that I gave you as an example, this non-decreasing sequence as an example, is not bounded because that's going to go up forever. Whereas maybe some of the other sequences, like the first one that we did, which was 1, 1/2, 1/4, 1/8, 1/16, and so on, that one is bounded because the terms were never going off to infinity or negative infinity. Cool. And then the other vocabulary term for the sequences would be a geometric sequence. A geometric sequence has the property that every term is obtained by multiplying the previous term by some fixed number. A classic one is one that we did earlier today, was 1, 3, 9, 27, 81, 243, etc., etc., etc. I just multiplied by 3 every single time. 3 was called the ratio, R for ratio. It's the ratio because take any two terms, divide the second one by the previous one. Take any two terms, and divide the second one by the previous one. They're all going to be 3. The ratio between any two terms is 3. So that was a geometric sequence. And so that one had a explicit formula of 3 to the power of n. That's what we mean by that, r to the n, where r is the ratio. Okay, and if your r is bigger than 1, like that example that I just gave, then the limit does not exist or might go to infinity. And we're going to use does not exist. We're going to use the word diverges. So this is an example of a sequence that diverges because it shoots off to infinity. Remember, if you get a finite number as an answer to your limit, then the sequence converges. Okay, all right, so that's geometric. Let's just do this example for a whole bunch of geometric sequences. So determine if the following sequence converge or diverge. If they do converge, find the limit of the sequence. So let me start off with this first one, and I'm going to use my calculator for that. I don't show the calculator, but maybe feel free to type it into your calculator as well. So I'm going to just, it doesn't tell me here. Let's just say I'm starting counting at 0. I think 0 is a common one. It might be 1, but 0 is a little bit more common. So if I start counting at 0, I got 1. And then 0.7 to the power of 1 gave me 0.7. And then 0.49 was to the power of 2. There we go. And then to the power of 3 was 0.343. And then to the power of 4 was 0.24. Sorry, not 4. 242401, etc., etc., etc. And then we can kind of imagine here what's happening. It's getting smaller and smaller and smaller because I'm taking a number that's smaller than 1 and raising it to a higher and higher and higher power. So it's kind of like that $1 in a million friends. You're definitely all going to be broke, right? It's going to go to 0. So I have my R in this case is 0.7. The limit of this sequence as n goes to infinity was going to be 0, which means that this sequence converges. Okay, for part B, you can start to notice for that one some very similar things here. My R in this case was negative 0.1. I would get 1, negative 1.01. And then if I were to do negative 1.01 to the power of 2, I got 1. Sorry, I typed that in wrong. There you go, 1.0201. And then if I did that now to the power of 3, negative 1.01, I would end up with negative 1.0303. And then I ended up with 1.0406, etc., etc., etc. And you can see what's happening now. It's alternating between positive and negative. That's called an alternating sequence. But the numbers themselves are getting bigger and bigger and bigger. Slowly, but they're getting bigger and bigger and bigger, right? So that one would be diverges. So this is a sequence that diverges, and it really diverges because R, the absolute value of R was bigger than 1. If the absolute value of R is less than 1, it converges. If the absolute value of R is bigger than 1, then the geometric sequence diverges. So same thing for this very next one right here, 2 to the n times 3 to the negative n. I'm going to give you the different colors so we can get used to that, is going to become 2 over 3 to the power of n. So my R is 2/3, which is definitely less than 1. So it converges and its limit would go to 0. You can use your calculator for that if you'd like. Similarly, for this one, it would be e over pi to the power of n. Feel free to use your calculator, but e is 2.7-ish. Pi is 3.1-ish. 2.7 divided by 3.1 definitely has a e over pi is smaller than 1, so therefore it converges. Whereas if I had it the other way around, pi over e to the n, my r is pi over e, which is 3 divided by 2.7, which is definitely bigger than 1, so that would diverge. So for the geometric sequence, it converges if your r is less than 1, and it diverges if your r is bigger than 1. So then, of course, something for that very last one there, I would rewrite that as e over pi to the power of n, but there is an extra pi on bottom. But my r is still the thing that's being raised to the power of n, which is e over pi, which is less than 1. So that one still converges. Cool. Cool. All right, we're doing really good. We only have one more example that I want to do for 5.1. This will be the last example. Okay, so let's say many people take aspirin on a regular basis. Suppose a person takes 80 milligrams of aspirin every 24 hours. Assume also that aspirin has a half-life of 24 hours, and what that means is that every 24 hours, half of the drug in the blood is eliminated. Okay, we're going to do part A, B, and C. First, find a recurrence relation. Then I want to use a calculator to see if I can estimate what's going to happen. And then I'm going to use calculus to confirm what my calculator told me. All right, we'll start off with part A. So for part A, I need a recurrence relation. And it's going to be kind of as obvious as it seems. I'm going to start off with just the numbers. Day 1, I take 80 milligrams of aspirin. So there is 80 milligrams in my bloodstream right now. And then the next day, half of it is gone, right? Half of it is gone because aspirin has a half-life of 24 hours and half of 80 is 40. But not only is half of it is gone, I take another 80. So now I have that. Now I have a 40 plus 80, and 40 plus 80 is 120. Now, one day later, half of that is gone. And then I take another 80 milligrams. So half of it was gone, which means there was 60, and then I have another 80, which now leads me to 140. And then the next day, half of it is gone, and I add another 80. 70 plus 80 is 150. And you can see what's happening here. Let's write this down as a formula. I'll just use maybe D because I think that was the vocabulary or the letter that they used there. So let's say D sub n plus 1, the next term, is 1/2 the previous day's amount because of the half-life. So whatever I had 24 hours ago, I now have half. But then I take another 80. So then I add another 80, where my first term, my first dose was 80. Okay, and then it did ask me, so for part B, it did say to use a calculator to see what's happening. So I'm going to do that. I'm going to use a calculator to see what's happening. So let me clear out from before, and I'm going to see what happens. Day 1, I had 80. Yeah, and then I cut it in half, and I added 80 for day 2. And I got 120. Okay, and then day 3, I cut it in half, and then I added 80. And then I had 140. Okay, that's cool. And then I cut it in half. I'm just going to use that answer button again. Cut it in half, added 80. And then I could just keep pressing enter. And then I press enter again because I have that answer now stored. Cut it in half, add 80. Cut it in half, add 80. Cut it in half, add 80. Over and over and over and over and over again. What does it look like it's settling down to? It's not really going above 160, right? I'm just still pressing enter. I got 159, no, maybe 160. Cut it in half, add 80. And rounded. All right, so it kind of looks to me like it's settling down at 160. So I used my calculator, and I'm working with the idea that it seems to me, my conjecture is the limit of that sequence is going to be 160. Now, part C was to confirm that using calculus. So here's what I'm going to do. I am going to let the limit as n goes to infinity of that sequence equal something. I think it's 160, but let's confirm. So I don't know what, let's pretend for a second I don't know what it is. I still think it's 160, but let's pretend for a second I don't know what it is. Then it would just be L. And if it were just L, then you would know that it doesn't really matter when you add 1 to infinitely large. So if the limit as n goes to infinity of d sub n is L, then d sub n plus 1 is also L, because it does not change anything when you add 1 to an infinitely large limit. Yeah. Okay, and I also have something from before. From part A, I have the recurrence relation for that sequence. And then I could take the limit as n goes to infinity, as n approaches infinity, of both sides of that equal sign and distribute it across. I'm going to take the limit of both sides of that equal sign and distribute it across. When I do that, on the left, the limit of d sub n plus 1, we called it L. On the right, the limit of d sub n, I called it L. So that would be an L. 1/2 is 1/2 and 80 is 80. All right, subtract 1/2 L to both sides of that equal sign. Subtract 1/2 L to both sides of that equal sign. And I have 1/2 L is 80, multiply both sides of that equal sign by 2, and I got confirmation that L really is 160. So that would be called maybe a limiting value, or the limit of that sequence. All right, there's a lot going on for sequences. 5.1 is probably the heavier section for sure. But there we go. That's the general idea for sequences, and we will do a little bit more for the next one. Thank you.